Welcome everyone. In this video we will look at histograms and histogram equalization. So we can represent intensity distributions of an image over the range of intensities from 0 to 255 using a histogram. If H is a histogram of a particular image, HRK gives us how many pixels have the intensity value RK. For example, intensity value 50. How many pixels have this? Maybe 5000 have intensity value 50, like that. The histogram of a digital image with gray values in the range 0 to L-1 in general is a discrete function HRK equals NK, where RK is the kth gray level and NK is the number of pixels having gray level RK. So what is this histogram in reality? So if you take images of your 8 intensities, and if you take every single intensity as a histogram bin with intensity 0, let's say we have 175 pixels, with intensity 1, let's say 290 pixels, let's say with intensity 2 we have 300 pixels, and so on up to 255. We may have 174 pixels, something like that. This is the histogram. So you can do different kinds of things. So we can combine intensities from 0 to 5 and put that in one bin and create a histogram with a coarser binning. All these things are possible. So we can even normalize this histogram by dividing by the number of pixels and have a probability mass function also. So the histogram that we described above has L bins. We can construct a coarser histogram by selecting a smaller number of bins L, like I described here. Then several adjacent values of K will be counted for a bin. So now let's do this small activity to construct this histogram for this 3x4 image. So it has 3 times 4, 12 pixels. So you can see that this is a 3-bit image, so the intensities are from 0 to 7 inclusive. So we'll create this histogram with intensity 0. How many pixels are there? 1, 2, 3, 4, 5, 6, 7. And then we have to do the counting with 0. No pixel is there with 0 intensity. 1, nothing. And with 2 you have this one, that's all. With 2 you have 1 pixel. Then with intensity 3 you have 2 pixels. So therefore you have to write 2 here, 2 pixels. Then with intensity 4 we have 2 pixels again, so 2 here. With intensity 5 we have 3 pixels. Then with intensity 6 we have 3 pixels, and with intensity 7 we have just 1 pixel. So when you add all these numbers in the histogram, 1 plus 2 plus 2, 5, 5 plus 3 is 8, 8 plus 3 is 11, plus 1 is 12, you must get, of course, the total number of pixels in the image. So this is the histogram. Now we can see how to calculate and display this histogram using OpenCV. So as usual we load these libraries and then we can read the image using CVImRead. So we read it as a grayscale image, and then the histogram calculating function is hist equals CV calc hist. So slightly cumbersome syntax. So I invite you to go to the OpenCV documentation and find out what these things are, but this will give me the histogram so I can plot it. So if we have a color image, if you open the image as a color image, then you have the BGR colors. So for each of the colors, I want to extract the histogram. So for I, comma C in enumerate color, we get the three colors written in this, and now histogram equals CV calc hist image I, and that's the index of the plane, and then you have the histogram, and then you plot it using that particular color. This is the way to get the color histogram. Okay, let's see in Python how to get this histogram. As we have seen, we import this, and then we read this as a grayscale image, and then we use the calc hist function, and this is the image. So cumbersome syntax, and then the zeroth plane, and the number of bits and so on you can specify. So read the documentation, and you can shift enter to run this. Alright, so this is the histogram. So what does this histogram represent? So you can say there are some dark pixels in this image, and some mid intensities, and some very bright pixels also. That's what it represents. So left hand side of the histogram is for dark pixels, and the mid tones, and the right hand side, very right hand side, is for the very bright pixels. So for the color image, you read this image as a color image, and then as we saw before, we have RGB in this tuple, and then we get the histogram for each of the colors. So I will be 0, 1 and 2, and then we plot them in those colors, in this color. Okay. Now we can think about image properties visible through the histogram. If the image has a dark histogram, many values in the left region will be there in the histogram corresponding to the dark pixels. If the image is a bright, not histogram image, the histogram will have many values in the right region that correspond to bright pixels. If a significant number of pixels are dark and a significant number of pixels are bright, the histogram will have two modes, one for the left region and one for the right region. Now, for example, if we take some picture fingerprint mark, so you can see this will be white and this will be black. So your histogram will have two modes like this, these corresponding to the dark pixels or black pixels, these corresponding to the bright pixels or white pixels. So a flat histogram signifies that the image has uniform distribution of intensities, then the contrast is high and the image will look vibrant. So sometimes the cameras also display these histograms. Sometimes they display all RGB 3 histograms so that the person who's taking the picture can do the adjustments in the camera itself to take a vibrant picture, so that he or she would not have to do the processing in a photo processing software. So now let's look at histogram equalization. So histogram equalization is to take an image whose histogram would be maybe not flat, maybe it has several modes, and too dark and too bright, and turn into a vibrant looking histogram image where the histogram is more or less flat. So a flat histogram. So this is the purpose of histogram equalization. Okay, to reiterate, photographers like to shoot pictures with flat histogram, as such pixels are vibrant. Histogram equalization is a gray level transformation that results in an image with a more or less flat histogram. So if you could not do that, you would employ histogram equalization. So we can take an image and make its histogram flat by using this operation called histogram equalization. So let's go through a set of equations and then understand how the histogram equalization operation generates a flat histogram, and then see how we can actually implement it. So consider for now that continuous intensity values of an image are to be processed. We assume that R is in 0 to L minus 1. So actually, usually L minus 1 in our case is 255, as you have seen. Let's consider the intensity transformation S equals TR. This is the input pixel value and this is the output pixel values. R is in the range from 0 to L minus 1 inclusive. That produces an output intensity level S for every pixel in the input image having intensity R. So there are two assumptions. TR is monotonically increasing in the interval from 0 to L minus 1. That means it does not decrease but increase continuously. And then TR, the mapping after mapping, what you get is would be also from 0 to L minus 1 for R being in this interval. The intensity levels in the image may be viewed as random variables in the interval 0 to L minus 1. So let PR, R and PSS denote the probability density functions of R and S. The fundamental result from basic probability theory is that if PRR and TR are known, then TR is continuous and differentiable over the range of values of interest. Then the PDF of the transformed variable S can be obtained using this simple formula. PSS is equal to PRR modulus dr by ds. Okay, remember that. All right, now let's consider the following transformation. That transformation is S equals TR L minus 1 times the integral 0 to R PR W dW. So W is the dummy variable. This is the integral of the probability density function of the input pixels. So PR, remember. Now the right hand side of the equation is the cumulative distribution function CDF of the random variable R. This function satisfies the two conditions that we have mentioned. Since it is an integral, it is always positive, and the integral of a function is the area under the curve. Equation 3 satisfies the first condition, that is, this is monotonically increasing. This is because the area under the curve cannot decrease as R increases. When the upper limit in this equation is R equals N minus 1, the integral value will be 1. Because the area under the PDF curve is always 1. So the maximum value of S would be L minus 1, and the second condition is also satisfied. Therefore, this expression satisfies both the conditions that we want. All right. Now to find PSS corresponding to this transformation, we use this equation. Now for that we need ds by dr. So that is dtr by dr. So we have to differentiate with respect to R. So when you differentiate with respect to R, we get L minus 1 PRR. Substituting this result in equation 1 and keeping in mind that all probability values are positive yields this. So PSS is equal to PRR dr by ds, and we get the value from here and put it over there, and then you can see it would become 1 over L minus 1. So what does this mean? So PSS is always, irrespective of S, 1 over L minus 1. That means uniform. L minus 1, uniform. 1 over L minus 1. So we recognize this form of PSS in the last line of this equation as a uniform probability density function. So that means we have carried out histogram equalization if you use TR of this nature. TR is this, we have achieved histogram equalization. Okay, so for discrete values, we deal with probabilities, histogram values, and the summation instead of a probability density function and integrals. The probability of occurrence of intensity level Rk in the digital image is approximated by Nk divided by Mn, where Mn would be the total number of pixels in the image. Nk is the number of pixels that have intensity value Rk. L is the number of possible intensity levels in the image, example 256. Recall that the plot of PRRK versus RK is commonly referred to as a histogram. The discrete form of equation 2 is, so sk equals L minus 1. So integral of, instead of the integral, we put the summation in this formula. And j goes from 0 to k, PRRJ. So then if you want to instead put nj, you have to divide this by mn and put summation nj. So thus the output image is obtained by mapping each pixel in the input image with the intensity Rk into a corresponding pixel level Sk in the output image using this equation. So this is just summing the histogram. This is actually the CDF. Okay, so let's do this example to understand how to implement this. Suppose that a 3-bit image L equals 8 of size 64 by 64 pixels, that is mn equals 4096, has intensity distribution shown in table 1, where the intensity levels are in the range 0 to L minus 1, that means 0 to 7. Carry out histogram equalization. So let's do this. So for intensity 0, we have the number of pixels 790. For intensity value 1, 1020, 3, and so on. So probability has also been given, but we don't need that. So we have to just keep on doing the cumulative distribution function. So here the summation from 0 to 0 would be 790, and 790 plus 1023 there. So that would give us I'm having trouble in doing a simple addition of numbers. So that would be 1813. To that we have to add 850. That would be 2663. To that we need to add 656, and we would get 3319. To that add 329. That would give us 3648. To that add 245. That gives us 3893. To that add 122. 4015. To that add 81. 4096. So for here you should get 4096, which is the total number of pixels. So then the formula dictates us that we need to multiply it by L minus 1 and divide by Mn. So L minus 1 divided by Mn, this would be 7 divided by 4096. So with this number, you have to multiply this, and then after that you have to round it off. So 7 divided by 4096 would be 0.00171. So with this number you have to multiply these things. So here you would get 1.35, and then 3.10, and you have to round that off to the nearest integer. So here you would get 1, here you would get 3. I should have had this calculation done. Sorry about that. .55 round it to the nearest pixel, so you would get 5 here, nearest integer. You would get 5.67. So write it as 6. .23, you would get 6 again. .65, write it as 7. .86, write it as 7. Get 7 here. So what this means is now that we have a table, so if you have an input intensity of 0, you write it, you map it to 1. 1, you map it to 3. 2, you map it to 5. 3, you map it to 6. 4, you map it to 6. 5, 6, and 7, you map it to 7. So therefore, we have the intensity transformation, and to the individual pixels in the image, you apply that. Okay, and then we can look at the code of doing that. So in this case, this is the histogram equalization code. So you have the NP histogram can be used in other than CV hist if you like. So take the image and write it as an array, and then can get this 256 bin histogram, the histogram and the number of bins, and then you can use sum to get the cumulative sum, and then to get the CDF you can to get the normalized CDF you can multiply by the histogram maximum and divide by the CDF max, and this using which you can draw the CDF, and then to do the histogram equalization you can do a CV equalize hist. So actually I'm using the OpenCV function here, but from the knowledge that we took from the previous slide, you can do it on your own also. So to get the CDF normalized, so you can do the same operation here again. Okay, let's look at the histogram equalization code. So I'm opening the shells image here, and then histogram and bins we compute, and the cumulative sum also, and the normalized CDF, and then plot the normalized CDF in blue, and then equalized image we obtain by cv.equalize hist, and of that also we get the histogram and the bins and the normalized one also, and then plot. So you can see the histogram of the original image. You can see it's quite dark because only pixels from value 0 to maybe 170 are there, and CDF is like this. But if you equalize histogram, you can see it's sort of uniform, not exactly, but this is what you're going to see. So here you can see the original image quite dark, but this one is quite vibrant after the histogram equalization. So you can see when you have the histogram equalization as a tool, you can make the images vibrant. So in summary, histogram is a distribution of pixel intensities from 0 to 255, like how many intensities are there for each of these values. And then equalization means trying to make this histogram a flat histogram so that intensities are equally represented so that you can get a vibrant image. Thank you.